I am on the grading team, and my partners are Matthew Camp and Nathan Beckman. And we're analyzing the aerator mixer system, and we're representing the UTC. In overview, I'm going to talk a little bit about our system's background, and then I'm going to show you our steady-state operating curve and step response results and analysis, and then our conclusions. This is a block diagram of our system, and as you can see, the system consists of an input of our motor power in percentage, and then it goes into the mixer drive system, and then an output comes out, and this output is a drive speed. This is a schematic diagram of our system. Our system basically consists in a motor that drives the gearbox and drives the mixer as well. Our input variable here then is the speed, is the percentage of the motor that's driving the mixer, and our output is the mixer speed that comes from it. This is a graph of our output versus time input with an input of 70%. As we can see here, our system reaches a steady state at about 3%, and then after steady state, there's close to 1200 plus or minus 8 RPM output. And well, we did this for intervals from 10% to 100%, and then from that graph, like the last one, we got the steady state operating curve. As you can see, our system's very linear. We have a linear fit there that shows a slope of 17.2, and it would be RPMs over percentage. And then that's about it for the SSOC. Then we had a step input laboratory. This is just to show how, the input comes in a step, not just linear. And we did this for 3 ranges. Each one of us had to do like 3 different ranges, and it was from 0 to 33%, from 33 to 66%, and from 66 to 100%. This is a step-up response graph, and it's from 70 to 100%. So we have a delta M of 30%, and then we calculated a delta C of 505.7 RPM. And then therefore we got a gain of 16.9 RPMs per percent. This gain, as you can see, it's pretty close to our 17.2 slope that we got from the steady state operating curve. Then this graph is the same as the one before, but for the dead time and time constant analysis. As you can see, our dead time is around 0.1 seconds, and our tau is 0.2 seconds, so they are very small in our system. This graph here is the same, but here it's for a step down, so it's from 100 to 70%, and then so our delta M is going to be negative 30, and we calculated a delta C of 507.5 RPM, and once again we got a gain of 16.9%. So again, our gain and both our gains in this analysis and on our slope in the SSOC are very close, which is good. And then in our tau and dead time analysis, again, we got a tau of 0.1, which is the same as before on the step up, and a tau of 0.3, which is pretty close as well, up to the 0.2. This is a graph of our average step response gains. We ran 3 trials for each interval, 3 trials going up and 3 trials going down. As you can see from this graph, I mean, our gain is pretty close overall. I mean, it varies from around 16.8 to 17.5, but in average, it's pretty close to the 17.2 that we got. As well as step response dead time, it doesn't vary very much, and it's once again really close to 0.1. It's very small. And our tau, it's the same. It varies a little. On the first interval, it was really constant, and then if you take an average, again, it's going to be around 0.3. So our dead time and our tau times were just very, very small. In conclusions, our SSOC showed a linear relationship between the system's input and output, and then the input operating range was from 0 to 100%, and our output operating range was from like 160 to 1700 RPM. The linear fit of the SSOC gave us a slope of 17.2, and in average we had a gain of 17.3 plus or minus 0.2 RPMs per percent, which is really close to the 17.2 from the SSOC. And then our dead time was around 0.1 plus or minus 0.02 seconds, and our average tau was 0.3 to plus or minus 0.2 seconds. Any questions?